Morning, everyone. My name is Snigdha Sarkar, and I welcome all of you to our Ansys Virtual Academy session today. Today's session is a special one because for the very first time, we will be talking about what Ansys can do for you if you're working with electromagnetic applications. We have with us a very special guest, Mr. Markus Kopp, who is an expert in the field, and he will be giving us a general overview of Ansys's electromagnetic simulation capabilities. Markus is a global technical manager at Ansys. In his 21-year tenure at Ansys, he has supported the Electromagnetic Suite, which includes a variety of tools such as HFSS, Maxwell, etc. He has held a variety of positions at Ansys, ranging from pre-sales support to territory management and marketing. Previously, he used to work at Sensormatic Electronics as a research engineer and Motorola as an antenna engineer. He holds 7 US patents and has written a number of published articles. So Markus, we are truly delighted to have you here with us today and really excited for the content that you will share with us. And with that, I'll pass it on to Markus. Markus, go ahead.
Thank you very much. Thank you for that very kind introduction. I am very excited to be giving this presentation today. The biggest reason is because I've been involved in electromagnetic simulation since graduate school. So this is the 1980s, mid-1980s, and I have always been a simulation guy. And I really like people to understand what is possible with electromagnetic simulation. And this is how we came up with this this particular presentation, which is really what is the state of the art when it comes to electromagnetic simulation. In other words, what is realistically possible to do with current technology. So hopefully at the end of this presentation, you guys will have a better understanding of what is possible and what is not possible. And obviously, as mentioned before, if you have questions, I'll be more than happy to answer them at the end. So please just write them down and I'll go through them at the end. So for the next 35, 40 minutes or so, I hope you guys enjoy the presentation, and let's get going. Okay, so with these types of presentations, I tend to start off with a little bit of history. So please forgive me, but I think it's good to put electromagnetic simulation into context. Electromagnetic simulation really didn't start until the 1960s, the late 1960s, when the first method of moment approach was used to solve electromagnetics. I'm starting in the mid 1980s because that is when Ansoft was founded. Ansoft is the company that pretty much pioneered electromagnetic, or was one of the pioneers of electromagnetic simulation. And the tool that most people use when they do high frequency electromagnetic simulation is a tool called HFSS, and that was released in 1990. And back then, tools are used to analyze simple structures. We'll talk a little bit more about that in a moment. And then as we go through the years, you can see that the capability of what is possible to simulate with an electromagnetic solvers have become ever greater, right? We've gone from single component simulations to multiple component simulations to what I call hybrid electromagnetic circuit simulations in about 2000, 2005. And of course, in 2008, Ansys acquired Ansoft. 2012, we started doing hybrid electromagnetic and circuit/system simulations. Then, of course, as part of Ansys, we started to integrate with the other physics like fluid dynamics and mechanical. So we have fully integrated electromagnetic, what I call reliant multi-physics simulations. In other words, the thing that we're investigating is primarily caused by an electromagnetic effect, although it could be in a non-electromagnetic device like maybe some motor or something like that, or a generator. And then, of course, now state-of-the-art, as I define it, is very large-scale electromagnetic circuit system combined or hybridized multi-physics simulations, and we'll see what that really is. So, as I mentioned in the previous slide, when HFSS was, or when electromagnetic simulation first got off the ground, we tended to only simulate very small things on the order of single wavelengths, right? With electromagnetics, everything is wavelengths. The more wavelengths your structure is, then the larger the model will be and the longer it will take to solve. So when we first started off, we could only really do small patch antennas, for instance. And then as we progressed through time, we started being able to solve what we would call medium-sized problems, which are basically, in this case, what we're looking at is a module, a radar module. So it has multiple antennas in the inside, possibly receive antennas and transmit antennas. And this is what we were doing about 10, 15 years ago. Of course, about 5 years ago, we got into what I call the very large electrical size, where we're now taking very small things like small antennas and placing them on the fascias of cars, or putting them onto entire fighter aircraft or civilian jumbo jets, what have you. So the size of what we are able to solve in an electromagnetic sense is increasing to hundreds of wavelengths in size, right? Maybe even low thousands. But where we are today is in the very large electrical size, which is really what we're looking at here on the screen, which could be an entire street scene with buildings and trees, other vehicles, right? So electromagnetic simulation has evolved from the very small to the very large, right? And that is shown on this slide here as well, where you can see that HFSS, which is our premier 3D electromagnetic field solver, in the early days was used to model things like that waveguide or possibly that inductor on the right, but everything was reasonably small, right? But of course, over time, we have better mathematics, better computational hardware, so we can start doing electromagnetic analysis on small aircrafts, things like that. And then now, of course, most recently, we can do an electromagnetic analysis on entire battleships, entire toll collecting structures that includes cars and trucks and all the information that is passed between them, as well as very, very small antennas onto very, very large structures like cell phone towers or military aircraft that have very small radar antennas or communication antennas. So we are no longer at a place now where we can only model very small things. We can actually model very, very large things. And when I mean model, we can give a very good electromagnetic description of what happens when you have these large structures, and you need to know what happens to them electromagnetically. So put that information a slightly different way. On the left-hand side, you can sort of see our single component simulations. This is what we used to do back in the day, right? We have a very basic waveguide components, very basic connector types or single antennas. And then of course, as we become better at simulating, as we get better hardware, and as the software matures, we now can simulate things like packages merged onto printed circuit boards. We can merge human bodies into simulations of MRI machines, and we can merge multiple single antennas onto an antenna platter or an array, complete with matching networks, attenuators, phase shifters, power dividers, what have you. So what we're looking at here on the left-hand side of the screen is sort of our capability circa 1998, and on the right-hand side is our capability circa 2012. And then sort of in the 2012s, what ended up happening is we started being able to make electromagnetic models of pieces of a system, and then recombine the individual pieces in a circuit simulator, and then thereby creating these hybrid electromagnetic circuit simulations, where we can take a very complex structure like the filter that's shown on the left here, this 8-pole filter We can break it down into pieces, do the electromagnetic analysis of the individual pieces, and then recombine them all together. And of course, what this allows us to do is allows us to rapidly tune things, because now we have smaller models, and it uses less resources because smaller models tend to solve faster. So we can make a bunch of smaller models that will then represent the larger structure. Now, the other thing that we started doing is mixing and matching electromagnetic simulations, not just with simple S parameter concatenation, which is we're doing on the left, but something a little bit more complicated, where we actually have real signals that are being driven into an electromagnetic simulation, so to speak. So on the right-hand side, you could see that we have if you look very carefully, it appears to be an RFID system, where we have a package and a conveyor belt at some distance from a wall where a sensor is mounted, and that is the electromagnetic simulation. However, we also have the corresponding circuitry for the transponder and the tag circuitry, and we create an overall simulation of that entire system, right? That entire RFID system, where we now not only take into account the electromagnetic behavior, but also how the system behaves under very specific electronic excitations. So this is sort of where we were in about 2017, 2016 or so. Now, when we move up into 2019, we've pretty much gotten our tools to the point where we can do what I would call some very interesting real-time analysis. What we're looking at here is we're looking at a simulation of a car driving on a road. Now, this is a full-size car. It has an actual radar module in the front of it. You can see that in the screen right here in the middle. To the left of that screen, what you are looking at is a Doppler range plot, which is created by our tool, right? So we do an electromagnetic simulation of the interaction of the radar system and the car that it is attached to, as well as other cars. And then we can take those results, those electromagnetic results, and we can then post-process them using our radar post-processing feature that's in the tool, and get these radar range plots, so that we can get something that basically looks what we're looking at here on the screen, which is a traffic scene that has multiple cars. We have traffic lights and street lights, and this is a dynamic model. And on the left-hand side, we can see all the radar images of all of the trucks and the cars, as well as some of the radar images from the various street lights, etc. So this is really sort of what I call a very large-scale electromagnetic circuit and system hybrid simulation, right? This now requires an electromagnetic simulation. However, we post-process data, just like a radar would shoot out. We post-process it to create these plots. So at the heart of all of our simulations, whether they are small or these very large simulations, sits a tool called HFSS. It's one of our premier electromagnetic solvers, and it is a tool that has been proven to be a highly accurate tool. Thereby, we are very confident when we use this tool in these very large simulations that the results are highly accurate. Although the reason why HFSS has these very high, this very good reputation for accuracy has to do with automatic meshing. I'm not going to go through the automatic meshing. However, I will say that we are one of the only companies in the world that does this very well. And it is the reason for why we have the reputation that we do. And if you have questions about the adaptive meshing, I will ask you to please ask me at the end, because this is a whole topic on itself. However, a point here is that please be aware that the key to HFSS and the key to HFSS is accuracy. And the reason why people who use our tools have an enormous amount of faith is because of this automated meshing. But let me show you, now that we've talked a little bit about what the scope is, what my definitions are, let me show you how we would use our tools to do some of this work. So the first example I'm going to use is using Ansys tools for ADAS design. So ADAS is automated driving, right, and assist. And the example I'm going to use here is a very simple 77 gigahertz radar array. Now, this radar array is designed using HFSS, and you can see it on the right-hand side, and you can see it has both transmit antennas on it as well as receive antennas. Now, the thing on the left where it says power divider in the light blue, that is our circuit tool. And what I've done is I have combined now, I've hybridized together an HFSS simulation, that's that square box that you see in the orange, and combined it with a circuit power divider, right? So now we have a hybrid simulation. And the reason why we're doing this is because when we're talking about radar antennas, they're steerable. How do we steer them? Well, we can steer them by changing the phase of the individual antenna excitations. So I've done all this in Ansys HFSS. And then the next thing I can do is I've now designed my antenna. I've created an antenna that is steerable. And the next thing I want to do is I want to integrate it into the front end of a car. And this is exactly what we're looking at here. So I've taken my antenna, which is a very small antenna. It's about maybe 10 centimeters by 10 centimeters. And I'm going to mount that in the front of this fascia of a car. And HFSS, of course, has a number of different tools within it, the circuit tool being one of them, the finite element solver being another one. And then we also have what we call our SBR solver, which I am now hybridizing into the simulation as well, so that I can do things like we're looking at here, where I have my fascia of the car, I've integrated my radar antenna onto it, and I can now do a very simple simulation of what does my antenna pattern, or what is the effective performance of my radar when it is sitting behind a fascia and when it is not sitting behind a fascia. And these are the first things that we need to figure out, right? If we put the antenna where it's supposed to go, how well does it work? So this is a very nice way for us to do this, right? But this is strictly an electromagnetic simulation, right? We're just simply saying that this antenna will work a particular way when we install it where it is. So the next thing we want to do is we want to figure out how well these antennas communicate with other antennas, right? For instance, or how well they pick up the radar signal. And we can do that as well here by just looking at a simulation where we have two cars communicating with each other. And you can see in the one instance on the left, the truck always stays in the left lane, whereas the instance on the right, the truck comes into the right lane, and we can see very clear in the results below that at some point the truck is going to impact what we call antenna to antenna coupling, but that is really rather just a measurement of how well these two antennas communicate with each other. And obviously when the truck goes between the two antennas, communication is going to suffer. Now, this is a dynamic simulation that we can do in our tools without any problem. But of course, we can take it to the next level, like I said, where we can talk about radar and how well a radar antenna will work. And we do that also in our post-processing in HFSS. And we've made the post-processing for that quite straightforward. Users simply have to specify the center frequency that they're interested in, the accuracy, range accuracy, the range maximum, velocity accuracy, and velocity window. And users can turn these knobs, and then we can tell you how well your radar is going to perform, your radar antenna is going to perform when we have these different variables. So then in the end, we can do some fairly sophisticated simulations like this one here, where we have a truck and a semi-trailer. The pickup truck is in front of the semi-trailer. They're both going at different speeds. we have our ego vehicle all the way at the end, down here in the right-hand lower right corner. And what we're really looking for is how well does our radar work in this kind of a situation, paying special attention to the fact that if you're in the ego vehicle, which is the vehicle behind the semi-truck, and we've all experienced this, we cannot see around the truck, so we do not know whether there is a vehicle in front of that semi-trailer or not. And then, of course, the question becomes one of, well, can our radar see it? And when we go through the simulation, right, we do our electromagnetic simulation of this scene, incorporating all of the cars in the roadway and the guardrail, we can see quite well on our range plot the radar echo for the semi-trailer, but we can also see the radar echo for the pickup that's in front of that semi-trailer, as well as we pick up the guardrail that's on the right-hand side of the road, right? So when we do these types of simulations, we represent reality, and we can very quickly and very easily see how discerning our radar is for potential obstructions and things like that, right? So what this allows our customers to do is it allows them to virtually test the performance of their radars for worst case scenarios, for corner cases, really for anything that might be hard to test or expensive to test. Certainly, you can test your software of your radar to make sure that it can pick up things that we know should be there or are there because they're part of the simulation. So it's a way for people to get a very clear understanding of how their radar is going to work. So that is one of our sort of key simulation types that we're doing because there's a huge amount of interest in ADAS. Now, the other example that I'd like to show you how we use our tools is really our 5G communication system design. So everybody's familiar with 5G. And as we all know, this has a lot to do with wireless high-speed or wired high-speed communication. So back in about 2014 or so, I created a simulation of an office that we can see this this office here. It has a wireless printer. It has a router. And the simulation was created to show that we can simulate digital communication between a router and a wireless printer. And back at this time, you know, this is when Wi-Fi first came out. So this was very much a state-of-the-art simulation where we included all of the necessary requirements to have a real live representation of a wireless communication system. So we settled on 802.11g, and we configured our simulation, and you'll see what I mean by that in a moment, to basically be an 802.11 Wi-Fi communication system that had exactly the type of modulation and encoding as well as error correcting at the receiver side that you would have in real life. And what this looks like in our tools is like this, right? On the left-hand side. So we have a transmitter block and we have a receiver block. And in our tool, I can create a Wi-Fi system using functional behavioral blocks that are in our library, and basically recreate all of the main stages of a Wi-Fi transmitter and a Wi-Fi receiver, right? Now, between the transmitter and the receiver, traditionally, people have some sort of element, right? Because there's a path that the signal has to go. So traditionally what people have is what they call a complex additive white noise element. And what that then does, it gives a little bit of reality to this system, right? It gives a little bit of, hey, something is happening to the signal between the transmitter and the receiver. So let's mock that up. Right. But of course, the problem with complex additive white noise is that it's just made up. It has no reality, it has no basis in the actual physical thing that you're trying to simulate. But we can use it to look at our orthogonal frequency division multiplex spectrum. We can look at our constellation plot, which is a QAM16 constellation plot. We can look at the system noise floor. So we can use this information to give us some sense about the ideal, how our system should work in an ideal case. But of course, here again are our ideal results. But what happens when we now, instead of having an idealized antenna and an idealized path between transmitter and receiver, let's put in some realistic pieces and parts. So here we have a P-PHY antenna. It's operates at 2.44 gigahertz, and this antenna gets analyzed with HFSS, or electromagnetic solver. And once we determine that the performance of the antenna on its own is good, we can then take the antenna and we can place it into a wireless printer, this one being courtesy of HP. And what we can then do is we can determine how well will this antenna work when it's inside the printer. And this is already very good information, but we can do more. But here, what we can see is that ideally what we would like to have for antenna results, installed antenna results, is we'd like to have these very smooth, sort of apple-shaped, what we call antenna patterns. Obviously, we can see on the screen here that the antenna pattern is not apple-shaped. And that's just what happens when you put antennas in structures that aren't meant to hold antennas. We all deal with this pretty much every day if you're an antenna engineer. But now, because we know the performance of the antenna has been compromised, we really need to figure out, well, does this thing still actually work, right? Can it still communicate with the router? And this is why I ended up making this simulation here, where we now have sort of a typical office environment where we have a router, we have a wireless printer, we have some file cabinets, right? And now the question really is, well, I don't have line of sight between my router and printer, so will this system actually work? And if I only used additive Gaussian white noise, I'd never be able to figure that out, right? So what we could do is we can replace our additive Gaussian white noise with an actual electromagnetic model of the environment where my high-speed wireless communication is taking place. So my office, right? So all I've done is I've replaced the additive Gaussian white noise block with an HFSS simulation block. Everything else is the same, and now I can look at the same results as before. And what is most interesting to me is that we can look at our constellation plot, and the blue dots represent sort of my initial attempt of creating this system where I just had additive white Gaussian noise and things were fairly well behaved. But once I put in an actual realistic environment, we can see that my constellation plot is starting, the constellation is really starting to drift, or it's being smeared around. Right? And this is a very clear indication that we're going to have a lot of dropped bits. Our signal to noise ratio has gone way up, and we're probably going to have a really, really poor bit error rate, right? So this, of course, is a simple example because it's an office, and hey, look, if I'm not going to simulate my office and see if my printer communicates, because I can just move my printer to a different location and it'll probably work. However, there are many instances when we can't simply change the location of our transmitter and receiver. Think of a nuclear installation, think of being in outer space, think of being subterranean or subsea. Once your transmitter is there, and once your receiver is there, it's very difficult to move them. And this is why we now enable our users to do these types of simulations, so that you can get some real life awareness of what happens. But remember also that I said that this was about 5 years ago, state of the art. So we've probably even made this situation better. And we have. And let me just talk about this as well real quick. Now, when I create these simulations, not only do I get to have the circuit information that I want, like constellation plots and things like that, I can also look at the fields that are in my space. And by looking at my fields in this space, it becomes very clear that my printer is in a bad location with respect to my router. We can see that there's very little field linkage between the two. So simply by looking at the fields, I can already tell that we're in trouble, right? So this is another thing we can do. So now we can look at the electromagnetic fields in our space, as well as our circuit type results, like bit error rate, noise ratios, things like that. But as I mentioned, this was like about 5 years ago. So what have we done in the last 5 years? Well, if you guys are following what's going on with 5G, you will know that 5G is going to take over the world. So we can use the exact same methodology that I showed before to do 5G design, with the addition that we can make our spaces much larger. Right? Before, I was only able to simulate this one single office, and now what I'm simulating is an entire apartment, right? Where I have a living room, a kitchen, bathroom, bedroom. And if we look at this picture very carefully, you'll see there's a human being in purple, and we have what's called a device or a beacon, and then we have our 5G array. Now the array is our transmitter. It's like our base station, or it's our router base station, right? And what we can now do is we can, because of the way 5G works, 5G is always looking for the best way to communicate, or the best communication path between device/beacon and our transmit array. That's part of the beauty of 5G, is that there's some smarts to it. And 5G antennas tend to be very, very directional. And if we look at this picture here, we have a very directional beam pointing directly at the device or the beacon. But we can model this now in a dynamic way where we introduce blockage. So if we have scene one, where we have no obstructions, no blockage, we can see that there's a very nicely shaped beam pointing directly at what we call our device or our beacon. And this, of course, indicates that we're going to have really good communication between those two devices. But now if a person is going to walk between the device and the beacon, what you'll see if you look very carefully is that this main beam is totally blocked by this human, right? But the 5G transmit network is smart enough to realize that there's blockage there, and a second beam, you can see it just off on the right hand side. This second beam gets a little bit bigger. Right on the left, it's small, gets bigger on the right hand side, and it's shooting not directly at the device, but it's actually shooting at the wall. And then it's going to use basically the wall as a reflector and reflect that signal to the device, right? This is how 5G works. 5Gs have a lot of MIMO. They employ a lot of MIMO, and they employ a lot of antenna arrays. And what they do is to have these dynamically steerable antennas. And we help people simulate those devices with those steerable antennas, right? So now a user of our software can go in and they can create any number of worst case scenarios or dynamic scenarios, and they can then see how well their antenna is going to work and how well their antenna will compensate for things like blockages. Right. So I'm looking at this in a slightly different way. It's the same room, same person, but now the person, you can see, has a little antenna pattern by his waist, and that is a cell phone antenna. And then we have we have what we call a target UE, or this is sort of our base station again. And what we can now do is we can help people work or improve their beamforming algorithms, right? So for instance, there's a beamforming algorithm that's called a zero forcing beamformer. And what that does, it dynamically steers the null of an antenna pattern in the direction of interference, right? So if you have an interferer and you don't want to waste any signal speaking with that interferer or projecting any signal towards that interferer, we want to have a null in that direction. And what we can see here in this particular simulation, you can see that the antenna pattern is changing as the person is moving through the room. And this is what your antenna, your 5G antenna, is doing dynamically, right? So the way we help people in doing these types of simulations is not just by letting them know what the antenna pattern is. For an ideal case or for a worst case, we can now dynamically tell our customers what the pattern's going to be, and we can help our customers determine how effective their beamforming algorithm is, right? So what I'm saying is that yes, we need electromagnetics because the behavior and the operation of our devices is dictated by electromagnetics, but we are now dynamically linking those results and helping people come up with better algorithms to make their antennas communicate more effectively when people are moving, when people are obstructing, when there's obstructions in the way. So this is a fairly large, I would say fairly sophisticated simulation, but this is still not the exact state of the art. The real state of the art is when we're looking at very large scale simulations, right? So here what we're looking at is the city I live in. This is Toronto, Canada. This is a downtown area. And if you look very carefully, we have down here this red blob, that's a base station. And over here is a little blob, a little yellow red blob, and that would be our car that has maybe a cell phone in it or something like that. And now, right, we are not just simulating two antennas, but we are simulating two antennas in an urban environment. And we're going to do this so that we can evaluate antenna array performance, we can do site evaluation, we can do our beamforming, our null steering, and we can discuss or describe how much antenna power is used, etc. So to give a little bit more insight into this simulation here, what we have is we have our base station, which is not moving, and our car that is moving. And if you look at the antenna pattern of the non-moving antenna, you can see that it is always pointing at the round sort of globe that is moving down the roadway, right? So this is dynamic beam steering. Right. So in order to stay in maximum contact, we need to steer that beam dynamically towards our source. And of course, this requires electromagnetic simulations as well as circuit simulation, as well as beam forming algorithms. And we can combine all of these things in our simulations. And we're talking about a very, very large volume here, right? We're talking about something that is 1 kilometer long or wide and 2 kilometers long. So it is a large, large system. And basically when we talk about received power, this is what we're looking at, right? The received power is all over the place because of all of the obstructions that are encountered and all of the multipath and all of the reflections that are encountered by the electromagnetic wave traveling from our transmitter to receiver, right? But this information is what is needed by people who want to make wireless communication systems. Now, in this particular case, right, we are using our SBR tool in combination with our HFSS tool. Our SBR tool is the tool that allows us to do these very, very large simulations, right? And because we can combine circuit and electromagnetic field solvers and beamforming algorithms, we can also look at things like base station handoff. We can see when does the power drop below a certain level, and it has to be handed off to another base station. Right, so we can see that right here. We have a dense urban environment. Our car is moving. There's our base station. And then we have a second base station over there. And what this allows us to very clearly show is that right here, where the blue and the red curves overlap, is where handoff is going to have to occur, right? Base station 2, the blue curve, we're good, right? We're far away from base station 1. But at some point, the signal that is received by the handheld device, right, is going to be equal from base station 1 and base station 2. And that's when we hand it off, right? And then right here, we're going to no longer be using base station 2 to communicate. We'll actually have been handed off to base station 1. And this is very, this is the type of information that, again, people need to know to do your worst case analysis, your corner case analysis, etc. So in the end, when we talk about what is the state of the art, it is really being able to simulate extremely large environments, right? Not just the connector or a waveguide, but extremely large environments, airplanes, cityscapes, and using those electromagnetic simulations in like in this case here, an end-to-end system example where we have our baseband transmitters, our RF transmitters, we have our receivers, and these are all electrical simulations. These are all electrical circuit simulations. And the most important part between the transmitter and the receiver, which is the channel, which could be an office, it could be outer space, it could be a moon base, a moon station, right? It could be really anything that where wireless signals have to go. That channel can be modeled from an electromagnetic perspective and include all of the electromagnetic behaviors that occur in nature: multipath, reflection, refraction, absorption, right? All of these effects are included in the electromagnetic characterization of your channel. So now you can get an actual virtual representation of the environment where you're going to have wireless communication, right? And we can make that as big or as small as we want, right? So when we talk about state of the art of electromagnetic simulation, what we're really talking about is taking electromagnetic simulation and putting it at the heart of our overall larger simulation, whether it's wireless communication or radar or really any other type of electromagnetic based component system, attaching the realistic drivers and the receivers, the transmitters and receivers, and making a virtual system, right? So we're no longer just using HFSS as modeling the antennas. It is important to do that. It is important to use HFSS to model antennas, but now we're combining it with the other type of simulation that is routinely done by electrical engineers, which is circuit simulation. And we are now at a point where we can duplicate reality to a point like we've never been able to do before. And when I mean duplicate reality, I mean we can virtually create any environment and describe it electromagnetically using our EM solver tools. And once we know that behavior, that electromagnetic behavior, we can incorporate it into a circuit simulation so that we have covered all the bases. We know what our circuit's going to do. We know what our electromagnetic environment is going to do. We know what those two things do when they're connected together. We have a virtual representation of an entire system. And that's the state of the art, modeling entire systems, modeling entire electrical systems. That's the state of the art. And if you guys have, so this is pretty much it for me. If you guys have any questions at all, I know I went through this material. It's a lot of material. I went through it pretty fast, but I hope you guys have some questions.
Thank you. Thank you so much, Markus. That was a lot of interesting information. I myself, I'm amazed at what Ansys can do for everybody who's dealing with either electrical or electromagnetic applications. So that was really informative. Thank you so much. Markus, when you talk about these extremely large environment simulations, the state of the art, wherein you're not just simulating large scale facilities, but also incorporating different systems. How does the simulation time or the computational resources required for carrying out such a simulation compare with small scale simulations? For example, the office room that you simulated, how would that compare to a simulation like the one you showed in the city where you have a lot of buildings?
Sure.
Would that be eased by the use of tools such as SPR or something of that sort?
Yeah, that's a great question. And the answer to that question is, when I did the office originally in 2015, I was limited in sort of how large a model HFSS could solve. I mean, it is there is a finite limit to everything when we're talking about HFSS and finite element solvers.
Right.
So doing something like a cityscape would be impossible. However, HFSS, the tool, as opposed to the solver engine, right? Because they're both called HFSS. We have an HFSS solver engine and we have an HFSS tool. It's a little confusing, but the tool itself incorporates a secondary solver, which is an asymptotic solver. That's called SBR, and it's through the use of this SBR solver that allows us to do these very large cityscapes and these very large, houses and apartments and stuff. It's a different solver than a finite element solver. It's an asymptotic solver, but it is the tool that since 17, 18 or so, has enabled us to do these very large simulations. So with respect to time, though, what I'll also say is that my original HFSS model of the office took a number of hours to solve. I'm going to say about 7 hours to solve. So it's a somewhat a lengthy simulation. Interestingly enough, with the SBR solver, because of how it is and what it does, I can solve that entire cityscape in less than an hour, right? So not only have we now the capability to do much larger simulations, we can do them faster as well, right? And the only thing we have to do is be cognizant of what the SBR solver is versus what an HFSS solver is and how they work differently. So we can do it bigger and actually faster now than I did 5 years ago.
That is really cool. That is really good to know, because I know that doing different kind of simulations, the bigger the model, the more time it takes. But unless and until you know about these extra tools that Ansys has to offer, it can be a little intimidating at first. But that Ansys has so much to offer, and you can use that to kind of ease your simulation efforts. So that is really good to know. And I think, we have some comments. I think people are really interested in presentations related to Ansys Maxwell, low frequency for motor design as well. So I thought, Markus, I'll let you know, just a comment, not really a question. And another question that I had, Markus, is the moving cars and, the moving human bodies. How are you incorporating that in your, electromagnetic simulations? This might be a simple question again, but I'm just, you know.
No, it's all good. Yeah, so the way we of course do it, right, is we do what I would call a stop frame motion. So if you're familiar with what they do in the cinema world, or in the cartoon world, they have this thing called stop frame, where basically you take a frame, right, and then everything in that frame, you take a picture, and then you move everything in that frame just a little bit, and you take another picture. And that's how we do these dynamic simulations. So we have a frame. So and in that frame, you might have, you know, 8 cars, and they're a specific distance apart from each other, and that's a snapshot in time. And then the next simulation will be a different snapshot in time, right? So we end up getting snapshots in time, and then we roll them all together as if it were sort of a dynamic. Well, it is dynamic, but the simulation is not dynamic. The
like
simulation
a flip book.
Is like a flip book, yeah.
Got
Exactly.
it. That makes so much sense. Yep. All right, Markus. I think we're out of time as well. But thank you so much, you know, for that wonderful presentation. It was really great to hear from you. And you know, if we have any feedback, please, you know, go ahead and fill out the survey, and we will be sure to incorporate your suggestions to improve these AVA sessions in the future. And yeah, we will post the next topic as soon as we can on the website, and hope to see you guys again soon in the next AVA session. Thank you, everyone. Thank you, Markus.
Thank you, everyone.
Thanks.
Thank you very much, and I look forward to speaking again. Thanks, everyone.